In Section 2 of this STEM instructional program, we will be discussing how an aircraft is controlled in flight. In subsequent lessons to this section, we will be introducing you to basic flight controls and surfaces in aircraft, additional flight surfaces that you might see on more advanced aircraft, and the basic flight surfaces and controls that would be found in rotary wing aircraft or helicopters. In order to start the discussion of flight surfaces and controls, we need to examine the concept of three-dimensional motion. To do that, we will start with the graph that most are familiar with. The graph typically used in math class is a coordinate system around a horizontal x and a vertical y axis. This graph provides only a two-dimensional perspective, but aircraft move in three dimensions. To show this, a third axis, the z-axis, is added. This projection shows the z-axis at an angle to show it on the page. In actuality, the z-axis would be perpendicular to the other two and point straight out of the page. If we were to look at an aircraft from three different perspectives, front, side, and top, we could see the relationship between these three perpendicular axes. Looking at the aircraft from a front or nose-on view, the x-axis would run through the wings, and the y-axis would run vertically through the cockpit. The z-axis in this case would project straight out of the slide. Looking at the aircraft from the side view, the y-axis would again run vertically through the cockpit, while the z-axis would run from the nose to the tail of the aircraft. Now the x-axis would point out of the slide. Looking at the aircraft from a top-down view, the x-axis would run through the wings, and the z-axis would run from the nose to the tail of the aircraft. Here, the y-axis would point out of the slide. In math class, we plot points on a graph to show position, or to draw two-dimensional figures. At some point, we even expand these drawings to three-dimensional shapes. For an aircraft motion, we will focus not on position or location, but on rotation around the three axes. These rotations are the focus of aircraft motion and on the basic design of aircraft control surfaces. The first motion we will look at is rotation around the y-axis. In terms of aircraft motion, movement around the y-axis is referred to as yaw. A change in yaw would cause the aircraft to either turn to the right or to turn to the left. We are most familiar with this rotation around the y-axis, as that is what we do in an automobile when we move the steering wheel to the left or to the right. While this is the only axis of motion for a car, an aircraft can be steered in two other dimensions. Motion around the x-axis is referred to as pitch. Changes in the controls that manage pitch would cause the aircraft to nose up or climb. A different change to these same controls would cause the aircraft to nose down or descend. Motion around the z-axis is referred to as roll. Changes in the controls that manage roll would cause the aircraft to tip or to roll to the left. An opposite movement of those same controls would cause the aircraft to roll to the right. To make an aircraft change direction, however, would require changes in more than one dimension. The flight of an aircraft takes place in three dimensions, so aircraft control surfaces must be able to provide for movement in each. To cause these motions, an aircraft must be able to rotate around its x-axis, y-axis, and z-axis. These rotations translate to yaw, pitch, and roll movements of the aircraft. In the other parts of this lesson on flight surfaces and controls, we will be covering how these motions are made and what structures on an aircraft and on a helicopter cause these motions to occur. In the first lesson to this section of our STEM instructional program, we discussed the basic concepts of aircraft motion and how an aircraft is able to move in 3 dimensions. In this second lesson, we will explore the mechanisms that aircraft use to move in these 3 dimensions. We will discuss the basic flight surfaces that cause an aircraft to change direction and how those surfaces are controlled by the aircraft pilot. As was introduced in Lesson 1, an aircraft moves in 3 dimensions that we modeled using a 3-dimensional graph with an X, Y, and Z axis. In particular, we looked at an aircraft rotating around one or more of these axes. Early aircraft had flight controls that addressed each axis of rotation that could be used separately or with other controls to make the aircraft rotate in more than one plane at a time. In order to cause a change in the direction of motion of an aircraft, an unbalanced force must be generated. By Newton's second law of motion, if we generate an unbalanced force, the object will accelerate in the direction of that force. To get this unbalanced force and the resulting change in motion, we must develop a structure that will change the flow of air around the aircraft. This is most commonly done by making the back end of flight surfaces movable. If that moving surface is kept at a neutral position, there is no disruption to the flow of air around the flight surface. If the movable surface changes position, an unbalanced force is generated. In the example that we have here, by causing the back end of the surface to deflect or rotate downward, we generate a force that is perpendicular to the surface that is moved. We refer to this force as the normal force. This normal force can be split up or resolved into 2 parts or components. The first component is a force that acts in the same direction as the flow of wind. We refer to this force as the drag force, which would act to slow the aircraft down. The other component acts perpendicular or at right angles to the motion of the aircraft. We call this force the perpendicular force. That is the force that causes the aircraft to change directions. In this case, the perpendicular force acts in an upward direction, causing the flight surface to rotate upward. If the control surface is rotated in the opposite direction, the normal force and perpendicular force are also changed. The drag force still acts to slow the aircraft down, but the perpendicular force now acts in a downward direction, which would cause the flight surface to also rotate downward. The first rotation that we will examine in this lesson is rotation around the Y or vertical axis. As we indicated in Lesson 1 to this section, rotation around the Y-axis is referred to as yaw. If we cause an aircraft to rotate around the vertical axis, it would cause the aircraft to turn to the left or to the right in much the same way as a car turns to the left or right. Yaw on most aircraft is controlled by a device called a rudder, which is located on the tail or vertical stabilizer of the aircraft. In many early aircraft, the rudder was the tail of the aircraft. In most contemporary aircraft, the movable rudder is located at the rear of a fixed vertical stabilizer. On many aircraft, a smaller movable control surface called a trim tab is also present. We will discuss the function of this control surface in the next lesson. The movement of the rudder is controlled by foot pedals located in the cockpit, commonly referred to as rudder pedals. The pedals in an aircraft have a completely different function than those in a car. The rudder pedals do the same thing in an airplane that the steering wheel in a car does. By moving the rudder pedals, we can change the heading of the aircraft or keep going in a constant direction. If the rudder pedals are kept side by side, the rudder stays at a neutral position and does not alter the flow of air around the tail of the aircraft, and the aircraft stays at a constant heading or direction. By pushing the left rudder pedal, the rudder is rotated in a clockwise direction. The normal, drag, and perpendicular forces are applied, with a perpendicular force pushing the tail in a counterclockwise direction, which causes the aircraft to turn to the left. By pushing the right rudder pedal, the rudder is rotated in a counterclockwise direction. The normal, drag, and perpendicular forces are applied, with a perpendicular force now pushing the tail in a clockwise direction, which causes the aircraft to turn to the right. By once again bringing both rudder pedals back to a side-by-side position, the normal and perpendicular forces are stopped while the drag force is minimized. The aircraft stops changing direction and remains on its new heading. Motion around the x-axis, or the axis that runs through the wings of the aircraft, is referred to as pitch. Again, as introduced in Lesson 1 to this section, pitch would cause the aircraft to rotate upward or to rotate downward. Pitch is controlled on most aircraft by movable fins located on the tail or horizontal stabilizer. These movable fins are called elevators. While there are two elevators on the tail of most aircraft, they work in synchronization with each other. The movable elevators are typically located at the rear of fixed horizontal stabilizers. Some aircraft also have trim tabs to support elevator function that are also located within the elevator at the rear of the horizontal stabilizer. In some high-speed, high-maneuverability aircraft, there is no fixed horizontal tail, and control surfaces are a single movable component called a stabilator or moving tail. We will discuss these and other flight surfaces in the lesson on advanced controls. The elevators are controlled in the cockpit by one of two types of controls, depending upon the type of aircraft. The cockpits of many aircraft contain control yokes that look similar to steering wheels in cars. Aircraft that have a higher degree of technology, and most fighter aircraft, have a control column that is similar to a joystick that you would find with most computer games. We will look at pitch control using the joystick first and examine how the control moves the elevators and changes the direction of the aircraft. With the joystick in the neutral position, the elevators remain in the center position, there are no normal or perpendicular forces, and the drag force is minimized. The aircraft maintains a constant direction. By rotating the control column forward, the elevators are rotated in a downward direction. The normal, drag, and perpendicular forces are applied, with a perpendicular force pushing the tail upward. This upward push on the tail of the aircraft causes the nose of the aircraft to rotate downward, and the aircraft descends. By rotating the control column backward, the elevators are rotated in an upward direction. The normal, drag, and perpendicular forces are applied, with the perpendicular force now pushing the tail downward. This downward push on the tail of the aircraft causes the nose of the aircraft to rotate upward, and the aircraft climbs. By returning the control column to the neutral position, the elevators once again return to the center position. The normal and perpendicular forces are eliminated, while the drag force is minimized. The aircraft would stop changing direction and continue on its current pathway, which could be a climb, descent, or level flight. Pitch control using the yoke is very similar to that of the joystick. With a control yoke at the neutral position, the elevators remain in the center position, there is no normal or perpendicular forces, and the drag force is minimized. The aircraft maintains a constant direction. By pushing the control yoke forward, the elevators are rotated in a downward direction. The normal, drag, and perpendicular forces are applied, with the perpendicular force pushing the tail upward. This upward push on the tail of the aircraft causes the nose of the aircraft to rotate downward, and the aircraft descends. By pulling the control yoke backwards, the elevators are rotated in an upward direction. The normal, drag, and perpendicular forces are applied, with the perpendicular force pushing the tail downward. This downward push on the tail of the aircraft causes the nose of the aircraft to rotate upward, and the aircraft climbs. By returning the control yoke to the neutral position, the elevators once again return to the center position. The normal and perpendicular forces are eliminated, while the drag force is minimized. The aircraft would stop changing direction and continue on its current pathway, which could be a climb, descent, or level flight. Motion around the z-axis, or the axis that runs from the nose to the tail of the aircraft, is referred to as roll. As introduced in Lesson 1 to this section, roll would cause the aircraft to tip either to the right or to the left. Roll is controlled on most aircraft by movable fins located on the rear edge of each of the wings. These movable fins are called ailerons. Unlike the elevators that work in synchronization with each other, ailerons work in opposition to each other. In other words, if one aileron moves upward, the other moves downward. The movable ailerons are typically located at an outboard position or near the wingtips. In some larger aircraft, such as commercial airliners, more than one aileron may be located on each wing. In other aircraft, ailerons may also be used as flaps for takeoff and landing. In these cases, these surfaces are called flaperons. On tailless aircraft, such as the B-2 bomber, ailerons may also serve as elevators and rudders, often referred to as elevons. We will discuss these and other flight surfaces in the lesson on advanced controls. Ailerons, like elevators, are controlled in the cockpit by one of two types of controls, depending on the type of aircraft. The cockpits of most civilian aircraft, commercial airliners, and heavy-lift military aircraft are controlled by a control yoke. High-tech aircraft and those requiring a high degree of mobility could be controlled by a control column. We will look at roll control using the control column first and examine how the control moves the ailerons and changes the direction of the aircraft. With the control column in the neutral position, the ailerons remain in the center position, there are no normal or perpendicular forces, and the drag force is minimized. The aircraft maintains a constant attitude. By rotating the control column to the right, the aileron on the right side of the aircraft rotates upward, and the aileron on the left side of the aircraft moves downward. The normal and perpendicular forces are applied differently on each wing. The perpendicular force on the right wing pushes the wing downward, while the perpendicular force on the left wing pushes upward. The combination of these two forces causes the aircraft to tip to the right. As long as the stick is kept in that position, the aircraft will continue to rotate in that direction. By rotating the control column to the left, the aileron on the right side moves downward, and that on the left side will move upward. The normal and perpendicular forces are applied, with the perpendicular force on the right pushing upward, and the perpendicular force on the left side pushing downward. This combination causes the aircraft to tip or rotate to the left, and to continue to rotate as long as the control column is held in that position. By returning the control column to the neutral position, the ailerons once again return to the center position. The normal and perpendicular forces are eliminated, while the drag force is minimized. The aircraft would stop its roll motion and continue on a straight pathway. This was not, however, return the aircraft to a level attitude unless it was either currently in level flight or rolled back to level flight. Roll control using the yoke is very similar to that of the joystick. With a control yoke in the neutral position, the elevators remain in the center position, there are no normal or perpendicular forces, and the drag force is minimized. the aircraft maintains a constant attitude. By turning the control yoke to the right aileron moves upward and the left aileron moves downward. The normal and perpendicular forces are applied, with the perpendicular force pushing the right wing downward and the left wing upward, rolling the aircraft to the right. By turning the control yoke to the right aileron moves downward and the left aileron moves upward. The normal and perpendicular forces are applied, with the perpendicular force pushing the right wing upward and the left wing downward, rolling the aircraft to the left. By returning the control yoke to the neutral position, the ailerons once again returned to their center position. The normal and perpendicular forces are eliminated while the drag force is minimized. The aircraft would stop its roll at whatever attitude it is currently in. Basic aircraft controls allow the aircraft to rotate around the y-axis or perform a yaw maneuver using a rudder located on the vertical tail, to rotate around the x-axis or pitch using elevators located on the horizontal tail, and to rotate around the z-axis or roll using ailerons located on the wings of the aircraft. There are a number of additional control surfaces that will be found on modern aircraft. Some of these controls will be discussed in a future lesson. In Section 2 of this STEM instructional program, we are discussing how aircraft are controlled in flight. In this lesson, we will be introducing you to the basic concepts of flight control in helicopters or rotary winged aircraft. While helicopters move in the same three dimensions that an airplane does, it accomplishes these maneuvers quite differently. This lesson will provide you with the basics of helicopter operations. There is significantly more involved than can be presented at this level. As was introduced in Lesson 1 to this section, an aircraft moves in three dimensions that we modeled using a three-dimensional graph with an x, y, and z axis. Basic aircraft controls allow an airplane to rotate around the y-axis or perform a yaw maneuver using a rudder located on the vertical tail, to rotate around the x-axis or pitch using elevators located on the horizontal tail, and to rotate around the z-axis or roll using ailerons located on the wings of the aircraft. A helicopter moves in these three planes just as an airplane does, but without many of the traditional flight surfaces. It might be easier to understand these controls if we looked at direction of motion in addition to rotations. More specifically, we will look at rotation around and motion along the y or vertical axis and motion within the xz plane. A helicopter is classified as a rotary wing aircraft. In other words, a helicopter does have wings, but the wings rotate around a central hub or hubs. A helicopter's main rotor or rotor system is the combination of several rotary wings or rotor blades and a control system that generates the aerodynamic lift force that supports the weight of the helicopter and the thrust that counteracts aerodynamic drag in forward flight. The main difference between a helicopter and a fixed-wing aircraft is the fact that both the lifting force and the thrust or horizontal force in a helicopter are generated by the same rotating blades. Directional and rotational motion of a helicopter is accomplished through three control mechanisms: a counter-torque control, collective control, and cyclic control, which will be introduced in this lesson. With a single main rotor helicopter, the creation of torque as the engine turns the rotor blades creates a torque effect. When viewed from above, the vast majority of helicopter rotors turn counterclockwise, creating a counterclockwise torque. By Newton's third law of motion, that torque causes the body of the helicopter to rotate in the opposite direction of the rotor motion, or in a clockwise direction. To eliminate this rotation, some sort of anti-torque control must be developed to allow the helicopter to maintain its heading and to provide yaw control. This is accomplished through a variable pitch anti-torque rotor or tail rotor. The tail rotor is a small propeller mounted so that it rotates vertically or near vertically at the end of the tail of a traditional single rotor helicopter. The tail rotor's position allows it to develop thrust in a horizontal direction. As it is placed at a distance from the center of rotation of the main blades, it produces a torque or rotational motion. One of the functions of the tail rotor is to counter the torque effect created by the main rotor. Tail rotors are simpler than main rotors since they require only collective changes in pitch to vary thrust. The pitch of the tail rotor blades is adjustable by the pilot via the anti-torque pedals. These pedals provide directional control by allowing the pilot to maintain a constant heading or to rotate the helicopter around its vertical or y-axis, changing the direction of the craft as pointed. The anti-torque pedals are located in the same place as the rudder pedals in an airplane and serve a similar purpose. They control the direction that the nose of the aircraft points. As the main rotor is constantly producing torque, the tail rotor blades must be set at a pitch angle greater than 0 to counteract this torque. When the rotor torque and the counter torque produced by the tail rotor are equal, the helicopter maintains a constant heading. To rotate the helicopter to the right, the pilot would depress the right anti-torque pedal, which would increase the pitch of the tail rotors. By increasing the pitch of the tail rotor blades, the torque generated by the tail is larger than needed to counteract the torque made by the main rotor. By Newton's second law of motion, the helicopter will rotate in the direction of the larger torque, which is produced by the tail rotor, or in this case, rotate in a clockwise direction or turn to the right. To rotate the helicopter to the left, the pilot would depress the left anti-torque pedal, which would decrease the pitch of the tail rotors. By decreasing the pitch of the tail rotor blades, the torque generated by the tail is smaller than needed to counteract the torque made by the main rotor. Again, by Newton's second law of motion, the helicopter will rotate in the direction of the larger torque, which is now the torque caused by the main rotor, and rotate in a counterclockwise direction, or turn to the left. Depressing the anti-torque pedal on the right increases the pitch of the tail rotor blades, and depressing the pedal on the left decreases the pitch of the tail rotor blades. This increases or decreases tail rotor thrust and makes the nose yaw in the direction of the applied pedal. It should be noted that the main rotor blades in French and Russian helicopters rotate in a clockwise direction, so work in reverse as far as increase and decrease in pitch are concerned. But in all helicopters, left pedals turn the helicopter left, and right pedals turn it right. To begin to understand how motion along the y-axis and motion in the xz plane is accomplished in a helicopter, we need to look at a concept called the rotor disc. The rotor disc is the area in which the main rotors operate. As the main blades rotate, they push the air in the rotor disc downward. The opposite force, by Newton's third law of motion, action-reaction, is an upward force on the helicopter itself. This upward force causes the rotor blades to flex or bend upward, which changes the location and, in some conditions, the tilt of the rotor disc. The helicopter uses this rotor disc motion and tilting to move along the y-axis and within the xz plane. The main drive of a helicopter is developed through a central mast. The central mast transmits power from the engine through a transmission to the rotors. Located around the central mast is a device called a swash plate. The mast runs upward through the center of the swash plate. The swash plate is actually made of two concentric discs or plates. The top, or rotating plate, moves with the mass and is connected to the rotor blades by connecting tubes, one tube per blade. The rotating plate is also connected to the individual plates through links that allow the tubes to change the pitch of the individual rotor blades. The bottom portion of the swash plate does not rotate. The non-rotating plate is connected to links that are manipulated by pilot controls, specifically the collective and cyclic controls. By use of these controls, the swash plate can shift vertically and tilt. Through shifting and tilting, the non-rotating plate controls the rotating plate, which in turn controls the individual blade pitch. The collective pitch control, or collective lever, is located on the left side of the pilot's seat and looks rather like an old-fashioned handbrake in a car. It is used to enable the helicopter to move along the y-axis or to climb and descend. The collective changes the pitch angle of all the main rotor blades collectively, or all at the same time, and is independent of their position in the rotation. Raising the collective lever causes the swash plate to move upward. This upward motion causes the connecting tubes to increase the pitch of all the rotor blades, increasing lift, which causes the helicopter to climb. Lowering the collective lever causes the swash plate to move downward, which causes the connection rods to reduce the pitch of the rotor blades. The rotor disc is lowered, and the lift provided by the rotor decreases. When the lifting force is less than the weight of the helicopter descends. Therefore, if a collective input is made, all the blades change equally, and as a result, the helicopter increases or decreases its total lift derived from the rotor. In level flight, this would cause a climb or descent. If the helicopter is not level, an additional motion is produced. If the rotor disc were tilted forward, backward, or to the left or right, the blades would still produce a force perpendicular to the rotor disc. As the rotor disc is now tilted, we must separate the force into two parts. The first force is the one that opposes the acceleration of gravity or pulls the helicopter upward. The second force acts perpendicular to the upward force. By Newton's second law of motion, this force would cause the helicopter to accelerate in the direction of that force, or move within the xz plane. To produce this tilting is the function of the cyclic control. The cyclic control, commonly called the cyclic stick or just cyclic, is similar in appearance on most helicopters to a joystick from a conventional aircraft. It is usually located between the pilot's legs, but on some helicopters it is a central pillar that either pilot can manipulate. The control is called the cyclic because it changes the pitch angle of the individual rotor blades as they rotate around the mast. Remember, for collective motion, the pitch on all of the blades is changed together, and the whole rotor disc moves upward or downward. To tilt the helicopter forward and backward, or sideways, requires that controls alter the angle of attack of the main rotor blades individually during rotation, creating differing amounts of lift force at different points in the cycle. As the pitch angle changes and more lift is generated, the blades flex upward. For cyclic control, the result is to tip the rotor disc in a particular direction, causing the helicopter to move in that direction. To produce forward flight, a helicopter's flight controls behave somewhat differently than those in a fixed-wing aircraft. Moving the cyclic forward causes the swash plate to tip forward. This causes the connecting rods to increase the pitch of the rotor blades as they move toward the rear of the helicopter and decrease pitch as they move toward the front. This action tilts the rotor disc to the front with minimum lift toward the nose and maximum lift toward the tail of the helicopter. When the rotor disc rotates forward, it produces a force acting toward the front of the aircraft. It also makes the nose pitch down, thus losing altitude, but increasing the rotor disc tilt and increases forward acceleration. A corresponding increase in collective control would be required to keep the helicopter from losing altitude. Coordinating these two inputs, forward collective plus increased cyclic, causes airspeed changes while maintaining a constant altitude. Moving the cyclic backwards causes the swash plate to tilt toward the rear of the helicopter. This causes the connecting rods to decrease the pitch of the rotor blades as they move toward the rear of the helicopter and increase pitch as they move toward the front. This action tilts the rotor disc to the rear with maximum lift toward the nose and minimum lift toward the tail of the helicopter. When the rotor disc rotates backward, it produces a force acting toward the rear of the aircraft. It also makes the nose pitch up, which increases the rotor disc tilt and increases rearward acceleration. A corresponding increase in collective control would be required to keep the helicopter from losing altitude as it moves backwards. To make the helicopter move to the left, the pilot would move the cyclic control to the left. Moving the cyclic to the left causes the swash plate to tilt to the left. This causes the connecting rods to decrease the pitch of the rotor blades as they move toward the left side of the helicopter and increase pitch as they move toward the right. This action tilts the rotor disc to the left with maximum lift toward the right side and minimum lift toward the left side of the helicopter. When the rotor disc rotates to the left, it produces a force also acting toward the left. It also makes the helicopter roll to the left, thus losing altitude but increasing the rotor disc tilt and increases acceleration to the left. Again, a corresponding increase in collective control would be required to keep the helicopter from losing altitude. To coordinate a left-hand turn, the anti-torque control must be added to move the nose of the helicopter in that direction. To make the helicopter move to the right, the pilot would move the cyclic control to the right. Moving the cyclic to the right causes the swash plate to tilt to the right. This causes the connecting rods to decrease pitch of the rotor blades as they move toward the right side of the helicopter and increase pitch as they move toward the left. This action tilts the rotor disc to the right, with maximum lift toward the left side and minimum lift toward the right side of the helicopter. When the rotor disc rotates to the right, it produces a force also acting to the right. It also makes the helicopter roll to the right, increasing rotor disc tilt and increasing acceleration to the right. Again, a corresponding increase in collective control would be required to keep the helicopter from losing altitude. To coordinate a left-hand turn, the anti-torque control must be added to move the nose of the helicopter in that direction. This same use of the cyclic and collective can cause the helicopter to move in any direction. Coupled with the anti-torque system, the helicopter has a wide range of motions not possible in a traditional fixed-wing aircraft. All the controls need to be carefully coordinated to make steady flight possible. It is this constant requirement for careful coordination which makes flying a helicopter difficult, at least in the beginning. Then, of course, there's learning how to hover. But that is another matter.